This is the course Electronic Systems and the lecture CMOS circuit design. After working through this tutorial, you should be able to design your own CMOS circuit. The prerequisites for this video is you need at least to have a basic understanding of the function and the principle of CMOS circuits. To show you how to design a CMOS circuit, we will use a simple example, and the example here is the following equation. And this actually is a typical task. There is a Boolean equation, a logic equation, and the task is to design a CMOS circuit which represents this particular equation. The question now is, how do we get a circuit out of this equation? Here we should keep in mind that in the final equations for the PMOS block and the NMOS block, the inversion bar is only allowed over individual variables like A or B or C, but not over whole expressions like we have it here, where the inversion bar is over the whole side of the equation. So the principle is to use De Morgan's law and to get rid of the inversion bar. So we can write again y equals, now we are using De Morgan's law, and by applying De Morgan we can write A and B. We put this in brackets or leave this in brackets. We put the equation bar over this expression. Then we have C with an inversion bar, and we change the OR to an AND. So that's applying De Morgan. If we look at this equation, we still have a problem, because here we also have an equation bar over an expression A and B. So again, we have to apply De Morgan, which yields y equals, now I'm writing A bar, B bar, so I have to change the AND into an OR, and I'm leaving the rest of the equation. So this is the final equation. And as we will see, this is the equation for the PMOS part of the circuit. Now we're going to derive the equation for the NMOS block. The NMOS block tells us when the output of the circuit is going to be 0 or low level. Thus, we need an equation with y bar instead of y on the left side. So what we have to do here is we have to use the original equation, and we are going to invert both sides of the equation. So I'm writing again y equals, and inverting the left side yields y bar, inverting the right side. If you look at the right side of the original equation, we have the inversion bar here. Inverting yields a double inversion, which cancels out. So we can write y bar equals A and B in brackets, or C, and that's it. So this is the equation for the NMOS block. Based on the two equations, the one for the PMOS block and the one for the NMOS block, we can start drawing the circuit. For drawing the circuit, we should keep in mind that if you look at the equation for the NMOS block, if we have an AND operation of two variables, then this corresponds to a series connection. If we have an OR operation between two variables or two expressions, we have a parallel connection. So we can start drawing the circuit right away. I have the two transistors with the input signal A and B in a series connection. And in parallel to this, I have the transistor with the input C. Of course, these are NMOS transistors, and I can already draw the output signal, which is Y in this case. Here again, I should remark that I left out drawing the wiring from the bulk contacts of the transistor to the ground. I did this just for the sake of simplicity, but in a real circuit, of course, the bulk contacts need connected to the ground. Now we can continue with drawing the PMOS block of the circuit. To do this, we have to look at the equation for the PMOS block, which tells us that we have a connection between the variables A and B with an OR, which is equivalent to a parallel connection, and this part of the circuit is connected by a series connection with the input C. So I can start drawing the circuit right away. Let me start with the transistor for the input signal C. And as I mentioned before, this is series connected to a parallel connection of a transistor A and a transistor with the input signal B. So I connect the upper part of the circuit with supply voltage or the battery voltage VB, and that's it. So we have the complete CMOS circuit right here. So last but not least, I should indicate that in the PMOS block we have PMOS transistors. So let me draw the bulk contacts, and again I'm not drawing the wiring of the bulk contacts to the supply voltage. I leave this out here for the sake of simplicity. There are two things we should note here in this circuit. First, we note that we have the same input signals for both blocks. If you look at the PMOS block, we have signal A and the same signal A, which goes to the corresponding transistor in the NMOS block. The same applies for signal B and of course signal C. So why is this? If we look at the PMOS equation, here we have the input variable A bar, B bar and C bar. But in the circuit itself, we have A, B and C. So the reason for this is that the PMOS transistor kind of inverts the input signal automatically. So if we have a variable A bar as an input in the corresponding equation, we need to use the inverted value, which is simply A, in the circuit. Second, we should notice that if we have a parallel connection, for example in this part of the circuit right here, we have a series connection in the other part of the circuit. The same applies if we look at this as a sub-block, then we have a series connection of the sub-block AB and C, and in the other block, in the NMOS block, we have a parallel connection of the sub-block AB and C. So this is typical for CMOS circuits because we have complementary circuits in the NMOS and in the PMOS block.